Hello and welcome back to Data-Driven Methods in Dynamical Systems. So, today I want to talk to you about something I thought was pretty cool. And so this is something that it's a phenomenon that ends up happening in science quite a lot, and is more or less the relationship between science and toys. This relationship was pointed out by Freeman Dyson in his book, Imagined Worlds, where he noted that improvements in computer technology really accelerated once we actually turned these things into toys. For example, once people started playing with computers, they wanted more and more sophisticated games, going from something like Pong to something like this, and then to ultimately something like this. Okay, I kid on the last one, but something like this. So consumer demand helped drive things like improved graphics cards, which can be used in scientific simulations when you're trying to tessellate an object and talk about finite element methods and stuff like that. It's used all the time in MATLAB to accelerate things because you have to do a lot of linear algebra in like 3D programming. Another place where we've seen these sort of improvements actually is in astronomy. So I don't know if you know, but every cell phone has a camera. And in this camera is a CCD. And the CCD was actually invented first to help with astronomy. Basically, if you're taking a lot of astronomical measurements before the CCD was invented, you had to use film. And so you had to expose film, choose the right film, and do all these other things. And then once you take that picture, you're done with it. That's it. I mean, you can analyze the picture and whatnot, but after a point, that is a whole physical object that you have to store or throw away. Once you introduce CCDs, this is now just a whole bunch of ones and zeros that can get stored on the computer's hard drive. And a single image can be compressed quite considerably to be practically nothing on a modern hard drive. Now, improvements in CCDs started happening back in the early 90s when you see CCDs starting to be used in consumer cameras. You have like the really early digital cameras. Say one, my dad had one that was made by Apple back in like 95, 96. And yeah, I mean, I don't even think that was like a single megapixel as far as its resolution. But within a decade, you have you have new things that are called cell phones, and on these cell phones they started having little cameras. And then once Apple introduced the iPhone, you started seeing much more sophisticated cameras in everybody's pockets. Now, these improvements in consumer CCDs and digital cameras all fed back into astronomy. Then now they have megapixel resolution CCDs that they can put into their giant telescopes. And if you're curious about what these giant telescopes look like, you should go check out Brady Heron's channel, Deep Sky Videos. I think he has like several channels, but I think this is the one. And so you should go take a look at that. And there he has whole tours of these places. And man, I wish I could go and check them out. So one common problem that we see in both consumer cameras and astronomical imaging is noise. If you want to take pictures of dark objects, you have to crank up the sensitivity of your CCD tremendously. And if you do that, then it becomes extremely light sensitive. So all your pictures will end up being grainy or muddy, and it's really hard to get rid of that noise to catch like a good signal. Naturally, this is an issue in astronomy because all of their pictures are long exposure pictures. So knowing how you can handle noise and get rid of noise is extremely important, and to save the pictures of your children, or to make scientific discoveries in astronomy. And the way that this is done is through what is called a PCA. We've actually already explored a PCA, and I didn't tell you that's what we were doing when we were looking at eigenfaces. So what we were doing with the eigenface database is that we were trying to extract what are called the principal components of the face dataset. Then we used these principal components to describe other faces, and we made what is called a face space. Now, What is PCA? Well, it's extremely close to the SVD. It's actually like kind of one half of the SVD. So the idea is that you start off with a data matrix. This is just like what we were doing before with the eigenfaces. Except in the eigenfaces, I really just opted to use column vectors. For each instance of data, I would throw them into a column inside of a matrix. And that aligns with Stephen Brunton's book in most cases. But Brunton decides to change his convention here, and this has been tripping me up, and this is like the 4th time I recorded this, because for the PCA example, he decides to stick to the convention that you see in statistics, where you put each row is going to be one of your data vectors. Okay, so what you do then, and we did this exact procedure with eigenfaces, is you take the average over all your data points. And so basically this means you're taking the average over all the rows. And then you take that average and you subtract it from each row. This is the same as, say, taking the data matrix and subtracting a column of ones times the average, which is a row vector, and then computing that. And so then you take that matrix, let's call that matrix A. From here, what you can do is you can go ahead and express the covariance matrix, where the covariance matrix is going to be A star A, divided by 1 over n plus n minus 1, where n is the number of data points you have. Now, what's nice is that this is what we call a covariance matrix, and the covariance matrix is a symmetric matrix, which means that it has a complete eigenbasis, and this eigenbasis is orthogonal. Now, the eigenbasis corresponds to eigenvalues of the covariance matrix, and we know that the eigenvalues for the covariance matrix actually are the singular values of the matrix A. We know that singular values are all strictly positive, and what we can do is we can go ahead and we can order them from greatest to smallest, and then that allows us to order the corresponding eigenvectors that come out of the covariance matrix. And in this case, what we see is that what we call the principal components, which are these eigenvectors, you can see which one has the most importance for our data, and that's one that corresponds to the largest singular value. And then as we descend in singular values, we have principal components that have less and less impact on our data, where the ones that correspond to very, very small singular values are very uncorrelated with the rest of the data set. And so the idea is that if it has a very small correlation, then it probably is noise. I mean, it could still be important for your data, but if you're looking to do some denoising or decreasing the amount of noise, one way to do it is to chop off a lot of the principal components that correspond to the smallest singular values. Now, what's cool is there's this application that takes it beyond just, say, denoising, and this is called PCA Tomography. And this is where you do an analysis of what are called data cubes. This is a concept that comes from astronomy, in particular radio astronomy, where you basically take a picture and you take the same picture in several different wavelengths. So you basically take, say, the same square, but you take a look at, say, the X-ray region, you take a look at ultraviolet visible spectrum, you take a look at radio frequencies, and this will give you this sort of stack of images that becomes a 3D cube. So each of them, you have your spatial coordinates and then one spectral coordinate where you take a look at the other wavelengths. Now, this is a tremendous amount of data to store, and it can be really noisy. So in 2009, Steiner and his co-authors, they wrote, they devised this technique called PCA tomography, where they use a PCA in order to decompose these data cubes, and it can simultaneously compress the data and find the principal components and also denoise it. And so this has become a technique that is getting used more and more, and it was also used to identify something new that we hadn't seen out of a particular system. So in particular, in his abstract, he says that they applied the method for illustration purpose only to the central region of the low ionization nuclear emissions region, Liner Galaxy NGC 4736. You gotta love names of these galaxies. And demonstrate that it has a type 1 active nucleus that was not known before. And furthermore, we show that it's displaced from the center of its stellar bulge. And so that's pretty cool. They used the PCA in order to discover something new in science that they didn't know before. and they can also store these things more efficiently and get rid of noise. Now what PCA does is it shifts the center to the center of your data collection. So basically you have a mass of points, and it moves the center point of your data to the origin. That way you can describe angles, vectors, describing your data a lot more effectively rather than trying to do something off in this direction. It puts it right in the middle, and then you can just look for orthogonal directions in each one stemming out from the origin. Now, this works really well if your data is, say, linearly described. So if you have like very, very elongated data, maybe it's an ellipse or something like that, then using regular PCA separates this data very effectively. But you run into problems if your data isn't really linear. Say you have data points that form rings around the origin or somewhere else. You still do the subtraction, move it to the origin, but then you need to figure out a different way of describing this data. And this is where kernel PCA comes into play. So kernels, and this is the first time we're talking about them in this class, kernels in data science are used to change nonlinear problems into linear problems by casting them into high-dimensional Hilbert spaces, or possibly infinite dimensional. We're not going to talk about what a Hilbert space is right now, but we can take a look at this from the perspective of of correlation. So just like before, where we talked about correlation, the correlation between two different vectors, you basically take away the mean of the data set, and then you take a look at, say, their dot product. Now, instead of taking their dot product, what we're going to do is we're going to replace the dot product with what is called a kernel. So the kernel basically effectively is implementing an infinite dimensional dot product where we sent our data points into what is called little l2, which is sort of this infinite dimensional column vector. Now, kernel functions are defined as being basically what we call these feature vectors, dot products with themselves inside of little l2. If you don't know what that is, that's fine. We'll build up to that. But the trick with the kernels is that you don't actually have to do anything in infinite dimensions. Kernel functions are often, the kernel functions that people care about are the ones that we can actually deal with. And these are ones that you can describe as just functions. And so, for instance, there's a Gaussian radial basis function that is extremely important in data science. There's polynomial kernels. There's the exponential dot product kernel, which I use all the time. And these kernel functions are very, very important in data science, and they allow you to turn nonlinear problems into high-dimensional linear problems. And so then you can change this ring, these rings, from being not that you can't really separate very well with using regular PCA, you can describe it very well if you do this sort of transformation with kernel functions. And so if you choose, say, a quadratic kernel function or a Gaussian kernel function, completely changes the look of the data from the perspective of machine learning. And so then you can use that to come up with some sort of PCA algorithm. Kernel functions sort of blur out your data points a little bit, and the authors like Shokov and others have methods of extracting the data points from their kernel descriptions. Now, this kernel PCA method has been used in medical imaging, like cleaning up MRIs and just general image denoising. And so I'm going to stop here now, and I'm going to break off into our longer lecture. If you just click the link at the end of the video or in the description, and we'll dive deeper into the PCA algorithm and kernel functions and kernel PCA. And if I have time, I'll try to throw together a MATLAB lecture on top of it, but we'll see. If I do, then that'll also be at the end of the video. All right, thank you for watching, and I'll see you next time.